Okay, so hi everybody. So today Davide is going to talk about a way how to check for a certain distribution if it's true, given the empirical observation of it. It's a problem that he encountered when analyzing complex web data. And
Thank you. So today we're going to talk about goodness of fit test for arbitrary distributions with unknown parameters. So many empirical quantities cluster around the typical value, and think about the speed of cars on a highway or the weight of apples in a store. But what happens is that even if these quantities vary somewhat, their distribution places a negligible amount of probability far from the typical value. And so this makes the typical value representative of most of observations. But there are distributions that do not fit this pattern very well. And while the fact that they do not fit this pattern are considered problematic or defective, at the same time they can be considered actually some of the most interesting distributions of all scientific observations. And in particular, what happens is that in the 19th century was first observed by Pareto that many processes do not follow the Gaussian distribution. And this led to the observation that the 80-20 rule is valid. It means that 80% of all effects result from 20% of all causes. So an example could be the fact that 20% of all employees are responsible for 80% of the productive output, or that 80% of all the wealth is owned by 20% of all population. And also, after the second half of the 20th century, all these observations about habitat distributions were used to characterize the other complex phenomena. As you can see in the slides, they can be used to characterize frequencies of unique words in documents. In this case, we tried to fit the occurrences of unique words in the Moby Dick novel by Neville, or also by the Barabasi work. Power law distributions or habitat distributions were used to fit empirical data coming from degree distribution of websites. In this case, we used the Notre Dame University as a representative of all the World Wide Web, as Barabasi did. Among these distributions, maybe the most used is the power law distribution, perhaps for its mathematical properties. So a quantity x obeys the power law if it is drawn from a probability distribution p of x, which is proportional to x to the minus alpha, where alpha is a constant parameter, which is called exponent or scaling parameter, and regulates the rate of decay of the distribution. And typically it ranges between 2 and 3, because if it is less or equal of 1, it can be a problematic distribution because it can't be normalized. And usually it's very not typical to find the power law distributions that fit all the empirical values that we can observe, but it's more usual to find power law approximation valid for values greater than some minimum x min, and in such cases we say that the tail has a power law decay. So we now give some brief basic definitions about the quantities involved. Power law distributions typically come in two flavors. So there can be continuous power law distributions, which can be described by a probability density function, p of x, which is equal to a constant c multiplied times x to the minus alpha, where c depends on the scaling parameter and on the lower bound of the power law behavior. Also, the power law distributions can be found as discrete distributions where the mass function is given by the probability of x to be equals to x is proportional to x to the minus alpha, and the normalization constant is given by the Hurwitz zeta function, which is which arises in nature very often. And now that we have defined the basic quantities involved in power law distributions, we need to find a way to estimate its parameters. So we start by estimating the scaling parameter just given the observed data. And for doing this, we need to assume to know the value of the lower bound on the power law behavior. And then later in the slides, we'll see how to give an accurate estimate of the lower bound, but for the moment, we assume it to be known. We choose to use the method of maximum likelihood estimation for the parameters alpha because it probably gives correct estimates of parameters in the limit of large sample sizes. And for the continuous case, we obtain an estimate which is given as a closed form expression, while for the discrete case, we have some troubles because we don't find any closed form expression. This is due to the fact that in the derivation of the estimate for the parameter is involved we need to numerically solve a differential equation in which is involved the first derivative of the Hurwitz zeta function. And then what we do is to give an approximation of the scaling parameter in the discrete case as if the observations from the discrete variable were drawn from a true continuous probability distribution, and then we round the observations to the nearest integer neighbor. It is proved empirically that this approximation gives quite good results for lower bounds greater than some empirical value. So, to assess the performance of these estimators, what we did is to use a non-parametric Bootstrap procedure, and then what we did is to generate a set of discrete data according to this distribution that you can see in the slide. So what matters is that the sample size is about 12,000, and that we generated discrete values of the variable between 2 and 29 with a non-power law distribution, and then we generated the tail of the distribution as a power law, where the parameters are 2.2 and x-min is 30. So if we should recover the true value of the scaling parameter by using the maximum likelihood estimation. So what we did is that for many choices of the value of x-min, so we started by the minimum value of the empirical data, and we made it vary till the value of the empirical data for which values greater than that x-min are more than 55% of all the empirical data, in order to have a pretty large data set on which fitting the distribution. For every x-min, we generated with the non-parametric Bootstrap procedure more than 2,000 datasets, resampling from our empirical data. And what we found is that as x-min increases, and in particular as x-min approaches the true value, which is 30, the scaling parameter tends to approach the true value, which was 2.2. And the stability, you can see in the zoomed square, is pretty good because the variance is very small. Okay. We now turn to the estimation of the lower bound on power law behavior. And what we decided to use is a minimum distance estimation. which is a statistical procedure which makes use of already established statistical tests and makes use of the statistics involved in the statistical test as if they were distances. The commonest is the Kolmogorov-Smirnov statistic, which computes the difference between the cumulative distribution function, where Fn is the cumulative distribution function on empirical data, while f of x is the theoretical cumulative distribution function. This is very used because you used to give very good results, but it places much importance on the center of the distribution, because in the limits both the distribution, the empirical and the theoretical, tends to be 0 and 1, so they tend to be equal. Another used distance is the Anderson-Darling statistic for a given cumulative distribution function. Is defined as in the slide, and while this statistic tends to give much more importance on the tail of the distribution, and so it could be a good choice for testing power law distributions on data. So x-mean will be defined as the point, as the observed data that minimizes one of these distances. In our case, we decided to use both, just to have an example on how they work. So the brown curve is the empirical CDF, so the cumulative distribution. The blue one is the cumulative distribution function using Anderson-Darling distance, and we find with Anderson-Darling distance an x-mean which is 30. While using the Kolmogorov-Smirnov fitting, we found that the x-mean, the optimal x-mean, is 35. Now, how can we test the power law hypothesis? So, we found procedures to give estimates of both the parameters, but they tell us nothing about the plausibility of the power law hypothesis. To do so, we need to, given an observed data set and an hypothesized power law distribution, we need to make a goodness of fit test, which is a statistical procedure which returns a p-value that quantifies the plausibility of the hypothesis. Why is it necessary? Because, as you can see in the slide, visualizing the log-log plot of the distribution is not sufficient, because it could be linear, even if it could seem linear, even if the distribution is not power law. As you can see, there I plotted a power law distribution and a log normal. Log normal is an heavy tail distribution which has a quadratic decay on the log-log plot, which is different from the linear decay of a power law distribution. So, how do we test our hypothesis? We do parametric bootstrap. Parametric bootstrap is a procedure which can be used to test our hypothesis, to get a p-value from a statistical test when parameters are estimated. So what we do is to fit our empirical data to the power law model, then we generate a large number, more than 2,500 of power law distributed synthetic datasets, with scaling parameter defined as the maximum likelihood estimation for the empirical data, and lower bound has the minimum distance estimation of the power law empirical data. These are the datasets, some of the datasets that I generated from our empirical data. Then what we do is to fit each dataset with its own power law model. Then we compute for each dataset the statistic, and then we compare what fraction of values of statistic are greater than the one that we observed on the empirical data. And using Kolmogorov-Smirnov test and Anderson-Darling test, we found that in the tail of the distribution, there are many fluctuations which made us reject the hypothesis of power law distributed. because as you can see in the empirical data, since the Anderson-Darling mainly focuses on tails, he rejects the hypothesis, and you can see there are many fluctuations. While we accept the hypothesis for the Kolmogorov Smirnov statistic because it mainly focuses on the center of the distribution. So what I suggest is to use both to have an idea of how the data are distributed more precisely. And we found our p-value because we made the choice to reject the hypothesis if the p-value is smaller than 0.1, which is really conservative, but I think that is necessary. And this is all that has been done for the power law distribution. What I found actually is that not all heavy tail distributions can be characterized by log normal distribution, power law distributions, because not all log decay can be characterized with linear decay. I found that many empirical data sets obtained from websites and degree distribution on websites follow a log quadratic decay, and so maybe log normal distribution could be better in these cases. But in literature, I couldn't find many methods for approximating discrete log normal distributions and on how sampling from discrete distributions. So at the moment, I'm focusing on defining sampling methods and discrete approximations for log normal distributions in order to have an idea of the evolution of my model in that case. And that's it. Thanks.
Parametric bootstrap, non-parametric bootstrap.
Okay.
Okay.
So okay, maybe I skipped. Non-parametric bootstrap is a procedure by which I can sample from my empirical data without any assumption on the distribution of my empirical data. So what I do is to uniformly sampling without replacement from my empirical data. Okay. And so I can think about a new data set as a data set from a new data set. While parametric bootstrap is obtained by some assumptions on the distribution which generated my observed data. So I needed to find sampling procedures for particular distributions in order to have a new data set. So in this case, for parametric bootstrap, what I did is to use my estimated parameters to sample data from a power law distribution with those parameters. And since I'm not interested in this part of the distribution, here I simply uniformly sampled from the non-power law distributed empirical data. So this is a semi-parametric approach. Okay. So parametric bootstrap is done mainly in the tail of the distribution.
Again, for doing semi-parametric, you need to have some assumption on what part of the distribution you care about.
Yeah, because I fitted the lower bound, so I know where to start to make a parametric bootstrap. Because I start sample from power law distribution whose lower bound is set at 30 in this case.
Before you show that basically if you try just to plot stuff and see if they're matching, it's not a good idea. But in the slide after, the one with the defensive, okay. The very tail distribution things seems to be messy, so I don't understand if they really behave. They really are kind of the same, or
so these you can consider these as fluctuations due to the random sampling procedure. So you have some noise, of course. So as there are more observations in the center of the distribution, you will have a similar behavior for all the new generated distributions, and it's more likely to have different behaviors in the tails because you have fewer observations.
Okay, so you have fewer observations because they're less probable. Okay.
Other questions?